Pluto is a distant and confounding minor planet, once considered a part of our planetary group's planetary family. However, recent alarming announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an amazing revelation. They suggested that this chill world is on an impact course with Neptune. Yet, how could this happen, and what might be the results of such a significant event? Are we seeing an intriguing cosmic eccentricity, or is there something else to this approaching limitless effect? Join us as we investigate the conceivable outcomes of a Pluto-Neptune collision. Pluto, a past planet that was downsized to a dwarf planet, is somewhat an enigma due to its odd orbit, and it remains a subject of interest and study in the astronomical community. As indicated by recent expectations from leading specialists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two planets, which could represent a critical risk to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires an unbelievable 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution yet. However, the interest doesn't stop there. Pluto's orbit is marked by its astoundingly curved shape, straying off altogether from the almost round orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination of 17 degrees to the ecliptic plane. The course Pluto follows is much steeper compared to other planets. One of the most interesting parts of Pluto's orbit is its crossing point with Neptune's. For something like 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, challenging what we'd expect from their positions in the planetary system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The investigation of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to determine its unique orbit. Unlike other planets, whose orbits lie mostly close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and curved shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three bodies like Pluto, Neptune, and the Sun move and affect each other through their gravity. Pluto's orbit is, in fact, turbulent. Minor deviations in starting conditions can lead to significant differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over especially long timescales, keeping tumult under control. Recent simulations have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Jupiter's massive gravity is strong enough to keep Pluto on a stable path for potentially billions of years. These quirks are essential in maintaining the order and consistency of celestial dynamics. Without these factors, our local planetary system would be a place of much more unrest and unpredictability. Pluto's orbit is a remarkable illustration of celestial mechanics at play, displaying both stability and chaos within our local planetary system. The unique characteristics of its orbit, influenced by the gravitational forces of nearby planets, especially Neptune, highlight the intricate and dynamic nature of space. Predicting major events, particularly when they involve turbulent orbits like Pluto's, presents tremendous challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainty. While numerical simulations offer a powerful means for understanding and predicting the future behavior of celestial bodies, they also highlight the limitations of our predictive abilities. So why are prominent astrophysicists only now raising concerns about a potential crash between Pluto and Neptune? Despite the various complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in astronomy, have expressed concern about a possible collision between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a captivating and devastating event in our neighborhood planetary system. The impact would release an immense amount of energy, probably breaking Pluto, given its smaller size and icy composition. Debris from the collision could scatter across the planetary system, potentially posing danger to other planets and their moons. For Neptune, such a collision could alter its current atmosphere and possibly its orbit, depending on the specifics of the crash. Michio Kaku, a prominent theoretical physicist known for his work in string theory, brings a unique perspective to the discussion as well. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics offer valuable insights into the mysteries of major phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital elements of celestial bodies like Pluto can yield important insights for future space missions. This knowledge can help in navigating the planetary system more efficiently, predicting potential hazards, and even planning missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. Regarding the physics of planets, celestial mechanics and theoretical physics are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that could potentially connect with string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, aims to explain the fundamental forces and matter in the universe. The collision could create extreme conditions of energy and gravity, possibly creating circumstances where predictions made by string theory could become detectable. For example, the high-energy impact could provide insights into the behavior of fundamental particles and forces under extreme conditions, a key area of interest in string theory. While the direct effect on Earth would be negligible due to our distance from the outer planetary system, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's confounding dance around the Sun continues to enrapture scientists and enthusiasts alike, offering a window into the complexities of celestial mechanics. While its reclassification as a dwarf planet sparked discussion and redefined our understanding of planetary bodies, recent discoveries about its orbit have reignited interest in its role within the local planetary system. Neil deGrasse Tyson and Michio Kaku, two distinguished voices in astronomy, have raised concerns about a potential crash between Pluto and Neptune, shedding light on the complex dynamics at play in our cosmic neighborhood. Their warnings emphasize the importance of understanding the gravitational interactions and orbital mechanics that govern celestial bodies' movements. Pluto's orbit, characterized by its unpredictability and steep inclination, defies traditional assumptions and challenges our view of planetary motion. Unlike the nearly circular orbits of its neighboring planets, Pluto's path follows a unique course, intersecting with Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, particularly Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over hundreds of years. Despite the turbulent nature of its path, numeric simulations and theoretical models play a vital role in predicting the future behaviors of celestial bodies and understanding the complex interactions between planets. These simulations show that while Pluto's orbit is turbulent over thousands of years, it remains relatively stable within the broader framework of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as proposed by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the ongoing uncertainties and intricacies in planetary dynamics. While such an event remains hypothetical and highly unlikely in the near term, the gravitational dance between Pluto and Neptune underscores the fragile balance of forces that govern celestial bodies within our solar system. Beyond its scientific significance, Pluto's study offers practical insights for future space exploration missions. The New Horizons spacecraft, launched by NASA in 2006, provided exceptional images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed stunning details of Pluto's surface features, including mountains of water ice and vast fields of frozen nitrogen, enhancing our understanding of the geological processes shaping the distant dwarf planet. The success of the New Horizons mission highlighted the technological advancements and collaborative efforts required for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies and the environmental conditions present in the outer regions of the solar system. These discoveries have implications for future missions to explore other dwarf planets and trans-Neptunian objects, furthering our understanding of planetary formation and evolution. Pluto's status as a dwarf planet has also sparked discussions about the criteria used to classify celestial bodies within the solar system. The debate over planetary classification reflects broader questions about scientific classification systems and the evolving nature of astronomical knowledge. While Pluto meets some criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet highlights the diversity of celestial bodies beyond the traditional 8 planets. Studying Pluto's orbit expands our knowledge of celestial mechanics and planetary dynamics to the outer reaches of the solar system. By examining the interactions between Pluto, Neptune, and other celestial bodies, scientists can gain further insights into the formation and evolution of planetary systems. These insights are crucial for developing theories about the origins of our solar system and understanding the processes that shape planetary bodies over billions of years. Pluto's discovery and subsequent study have contributed to our understanding of planetary migration and the formation of the Kuiper Belt, a region beyond Neptune populated by small icy bodies. Studying Pluto's orbit provides clues about the gravitational interactions that may have influenced the formation of planets during the early stages of the solar system's evolution. Understanding the complexities of celestial mechanics can also inform future space exploration missions, including the search for habitable worlds beyond our solar system. By studying the motions of distant celestial bodies, astronomers can identify potential targets for future exploration and assess the feasibility of traveling to other star systems. The potential impact of a Pluto-Neptune collision, while highly unlikely, serves as a reminder of the dynamic nature of the universe and the unpredictability of cosmic events. As we continue to explore the outer reaches of the solar system and beyond, the study of planetary orbits and celestial mechanics will remain a central focus for astronomers and space agencies alike. Pluto's orbit, which deviates significantly from the idealized paths of other planets, offers valuable lessons about the complexities of planetary motion. The stability of its orbit over long time periods, despite its eccentricity, provides important insights into the balance of forces that govern the movements of celestial bodies. In a sense, the ongoing study of Pluto's orbit and potential interactions with Neptune reflects the broader challenges of understanding the universe at large. With each new discovery and each theoretical model, we continue to refine our knowledge of the cosmos, uncovering the mysteries of distant worlds. As we delve deeper into the peculiarities of Pluto's orbit, it is crucial to understand how such a remote body remains in a delicate balance within our solar system. Despite its small size and distance from the Sun, Pluto's gravitational relationship with the other planets, particularly Neptune, is an example of the intricacies of celestial dynamics. The influence of Jupiter, the largest planet in our system, plays a significant role in stabilizing Pluto's orbit. Jupiter's immense gravity creates a sort of cosmic anchor, preventing Pluto from drifting too far off course over millions of years. Interestingly, Pluto's relationship with Neptune, although seemingly chaotic, is actually in resonance. This resonance ensures that even though their orbits cross, the two planets never collide. This phenomenon is known as a gravitational resonance, which occurs when two orbiting bodies exert regular periodic gravitational influences on each other, creating a stable orbital relationship over the course of their orbits. Pluto and Neptune will always remain separated by a certain distance thanks to this resonance. It's a delicate system that has prevented any catastrophic interaction so far, despite the close crossing of their paths. This resonance is part of the reason why a collision between Pluto and Neptune is considered highly improbable. Though the possibility of slight disruptions over extremely long timescales cannot be fully ruled out, it also highlights how dynamic systems in space can evolve in unexpected ways. While the orbits of most planets and moons appear relatively stable, the interactions of more distant bodies like Pluto are still subject to complex gravitational forces that could change over time. Therefore, even though the scenario of Pluto colliding with Neptune remains largely hypothetical, it underscores the ever-changing nature of planetary mechanics. In addition to these gravitational relationships, the study of Pluto's orbit provides key insights into the early history of the solar system. Many scientists believe that Pluto's current position and orbital characteristics may be remnants of an ancient phase in the solar system's evolution. Early planetary migration, possibly caused by the gravitational influences of the gas giants, might have altered the orbits of many smaller objects, including Pluto. This history is crucial for understanding the formation of the Kuiper belt and other distant objects in the solar system. Further exploration of Pluto's orbit and the gravitational interactions with Neptune could also shed light on the broader processes that shaped our solar system structure, offering valuable lessons for the study of exoplanetary systems and their evolution.